Okay, so today we are starting hybridization. We have one column in your little table that we still need to fill out. So to describe that, before we actually fill the column out, just go ahead and turn to the diagram in your notes that looks like this, these crazy looking pictures here. I really kind of want to move this. Come on. Okay, so up to this point, we've really never talked about how bonding really happens. I don't know if you guys have ever been kept up late at night wondering how S's and P's bond. I'm sure that keeps you guys up. Yeah? Sleepless nights, Julian? Yes? Okay. Well, we really haven't gotten into the whole concept of hybridization. When I say hybrid, what do you guys think of? Cars, okay. Yes? I've heard no one mention biology, which is sad. A liger. My favorite animal on the planet is a zonkey, by the way. So there is a free A in my course if you get me a zonkey to take a picture with. That's my goal, is to take a picture with a zonkey. Seriously. So free A in the course for anyone who can get me a zonkey. Man, greedy. High A or low A was the question. Depends how many stripes the zonkey has. If it's extremely striped, yeah, I want. Oh goodness. Okay, so back on task here. When things bond, the orbitals basically mix up to make entirely different orbitals. So the existence of S and P's when things bond are no longer. What happens? So I'm starting with the tetrahedral family because it's the easiest one to do. So on this first picture, this is the electronic tetrahedral situation. It doesn't matter what day it is. I can't spell pretty much any day. Tetrahedral, rain or shine. I can't spell. All right. This is the tetrahedral electronic structure. And we know that if we're tetrahedral electronically, how many areas do we have around the central atom? 4 areas. I'm starting with this because it's the simplest. So if we have 4 areas around the central atom, we need to pull from 4 orbitals. When we bond, we pull from valence orbitals. What are our valence orbitals? S and 3 P's, right? Okay, so what actually happens, all these orbitals are thrown into a big pot. They're mixed up, not literally. There's not someone over a pot mixing orbitals, but they're all thrown into one big pot, mixed up, and we get 4 brand new orbitals of kind of average energy between the two, okay? And each one is called Sp3. So we start with our 3 P's and our S mixed together, and we get 4 brand new ones, each one called Sp3. I want to make it clear that one is not S and the others are P's. Each single orbital is called Sp3. And these orbitals are 109.5 degrees apart from each other. So when we talk about bond angles, we're talking about the bond angles actually of the hybrid orbitals. We're not talking about of some random S's and P's. S's and P's are gone once the bonding starts. Okay? So anywhere you have 4 areas of electron density around the central atom, the hybridization is Sp3 hybridization. And we have 4 orbitals, each with that name. So go to your table, and I'm not going to go to it yet. We're going to fill it. I'll fill it in at the end. But anywhere you see 4 areas, tetrahedral, trigonal planar, and bent, your hybridization is Sp3. And how it looks is Sp with a superscript 3. So that you know where that table is. So now when we move on to 3 areas, things get really a little bit exciting. When we are creating a situation where we need 3 areas, 3 bonding, or 3 any areas around the central atom, we're going to utilize 3 orbitals. Okay? What 3 are we going to utilize? S and P and P. So we throw all these in a pot together, mix them up, and we get 3 brand new orbitals, each called Sp2. Here are the 3 orbitals, Sp2, Sp2, Sp2. How far apart are these? 120. Okay? Now what about this? This guy. That poor little P, we call him unhybridized. He's gonna wreak some havoc. I've looked it up. Both are acceptable. Wreak, seen them both. he's going to wreak some havoc on the situation, and he's going to end up causing double or triple bonds is what he's going to do. And I'm going to explain how when we get to drawing these funky orbitals. But just know that he's there and he will take part in it. Okay? All right. So go to your table under SP, for anything that's trigonal, planar, or bent in the 3 area, go ahead and write the hybridization of what? SP2. And I'm talking total areas, not just bonded areas. Total areas. Okay, the last scenario we're actually going to look at pictures for would be 2 areas. If we have 2 areas, we're only going to utilize 2 orbitals to make our hybrid. And we're going to mix those together, and we're going to get 2 brand new orbitals called SP. There's one, and there's the other. So there's our 2 P's. What are these 2 P's alone called? Unhybridized. Good. How far apart are these orbitals? 180. And I failed to mention this on the previous slide, but do you see how there's 2 P's here? Those are my unhybridized P's right there, hanging out, ready to cause problems. On the previous slide, I didn't show you. I forgot. And all this stuff is in the way. It's fabulous. This is also your unhybridized P right there, this guy. All right? And again, they're going to cause the creation of double and triple bonds. Everyone good? Now, I want you to skip to, well, no, let's go ahead and finish filling the chart in. So for review real quick, 2 areas has what hybridization? SP. 3 areas has SP2, so we've got those 2. 4 areas, SP3. Now, what happens to our octet when we get to 5? What's going on? Expanded. Because we're expanded, we have to draw from something other than S's and P's. Okay, what are we drawing from? D's. Good. So, if we need 5 areas, we need 1 more orbital, and it's going to be a D. So, guess what the hybridization is for this one? Good. SP3D, and that's for all our 5s. And what about this last one? SP3, good. We're going to pull in another one. Now, it's as simple as that, guys. We don't draw the pictures with the D's. It's because it's impossible to draw, being a 2-dimensional mind that we have, to draw it otherwise without the use of a computer. But not to mention, I wouldn't even know where to start. So what I want to do, though, is talk to you about bonding. To get there, I want to skip some of these problems. Here you have a page describing what we call pi and sigma bond. I'm going to explain this as I do my drawing. So right now, skip all the way to the page that has just ethane written on it. We're going to draw ethane with all the hybrid orbitals and talk about sigma and pi bonding. So what is ethane? What does it look like? Let's draw the Lewis dot. 2 C's and then all H's around. So we're going to draw hybrid orbitals and show how things actually bond. So you're going to have to be patient with my lack of drawing skills because I can't draw. So how many areas are around each of those carbons? 4 areas. So what's the hybridization? Sp3. So we agree there's 4 brand new orbitals around the C's that are called Sp3. So I'm going to kind of draw that. So I have the carbon on the left. There's an Sp3 there, an Sp3, an Sp3. These are actually 109.5 from each other in a tetrahedral shape, but I can't really draw that. So I'm going to do Sp3, Sp3, Sp3. And then my other carbon, here's where the bonding happens. My other carbon is here. It's going to have an overlap head-to-head of this one Sp3 with that Sp3. And we still have 3 more Sp3s for our 4 new orbitals around that carbon. Okay, what about the hydrogens? Tell me about hydrogen. How many electrons? 1. Tell me about orbitals. How many orbitals are there? 1. Is there any, or are there any orbitals to mix? So hydrogen really can't make a hybrid of its own. It's only contributing its s orbital. So when these hydrogens all make this bond here, they literally just have their s orbital overlap with the hybrid from each carbon. So we have our hydrogen there, our s orbital there, and it's a head-on-head overlap as well. And S stands for the orbital, not the element. So there's all my hydrogens. Now let's talk about the bonding. Anytime you have a head-to-head overlap, known in the Lewis dot structure as just a single bond. Anytime you have a single bond in a Lewis dot, which is what all of these are, right? Aren't those all single bonds in our Lewis dot structure? Single bond in Lewis dot. We call it a sigma bond. I'll talk about the other one later, but anytime you have a single bond in a Lewis dot, it means the orbitals are just touching head to head. It's a sigma bond. So how many total sigma bonds are in ethane? 6 sigma bonds. Okay. So 6 is actually incorrect now that it's been brought to my attention because we have another overlap. Where is that? It's between anytime, let me repeat, any single bond in your Lewis dot structure. Look up there. There are the 6 for these. There's also one here. So those are all sigma bonds. So there are 7 sigma bonds. Got it? Okay. Let's go ahead and draw the next thing. Let's draw ethene. What's different about ethene? It's got a double bond. So C, double bond. C, how many H's on each carbon? 2. I need to talk louder because everyone at home thinks I'm talking to myself. All right. So what's the hybridization around each C? We got sp3 around each C, right? So how many orbitals then are surrounding C in this case? 3 sp3s, right? But what's missing? If we have sp3, what also do we have? Just kind of hanging out, not doing anything? Don't we have an extra? This is not sp3, guys. Here we go again. Oh my goodness. It's what? sp2. Yeah, you are now, because when I record, I'm like listening to what y'all saying, write it down. So you have been shunned from talking. No more speaking for Jasmina. sp2. It's 3 areas. 1, 2, 3. So the hybridization is sp2. Is everyone good with that? I'm a little concerned that everyone was like, were y'all not remotely confused when I did that? Okay. Well, I'm glad to hear that. Speak up then. So, sp2 hybridization. What is left undone? We have an unhybridized P, don't we? I'm going to show you what that unhybridized P does. Hybridized P. All right, so to draw these, what we have is a C, and we've got 3 sp2 orbitals hanging around each. sp2, sp2. I just have a weird feeling like an alarm's going to go off all of a sudden. It's really weird. It's probably not. I don't know. It's just a sensation I have. Okay. So around this one we have 3. And how far apart are these orbitals that I'm drawing? 120. Good. But don't forget, because this is sp2 hybridized, what do I have? An unhybridized P on each carbon. So I'm just going to draw it like this, okay? So what happens? The lobes kind of reach sideways, making a ring. So imagine a synchronized swimmer. I'm going to do a little gesture here for those of you at home, going like this. That's what is going on there. So the sideways overlap here is called a pi bond. The head-to-head overlap is called what? A sigma bond. So, to simplify this, a single bond in any picture is a sigma. A double bond is a sigma and a pi. Make sense? So how many sigma bonds are in this picture? Well, I forgot to draw the hydrogens. That would help. But yeah, 1, 2, 3, 4, 5. So 5 sigma bonds. And how many pi's? 1 pi. And really right now, the only thing that's going to make your pi bonds are your unhybridized p's. So where are we going to only see, well, how many areas will we only see pi bonds in? 1 and 2 areas. No, 2 and 3. Here we go again.
I didn't say that.
You didn't, but now I think I'm going to, Hannah's next.
I talked you through.
2 and 3. And 2 areas, we've got 2 unhybridized p's, right? 3 areas, we've got 1 unhybridized p. So those are going to be the places we see pi bonds, which totally makes sense because when you have those double and triple bonds, that cuts down on the number of areas around the central atom. Okay, so the next one we're going to draw, let's do it with no mistakes this time. How about that? Ethine. See, what's the difference with this one? Triple bond. And then we have 1H on each of the C's. All right, here we go. What's the hybridization for 2 areas around each of these? Sp hybridized. So how many unhybridized P's do we have? 2 unhybridized around each of those carbons. So I'm going to draw it out. We've got a C and a C. We only have 2 hybridized orbitals, so each one is called what? Sp, Sp. We've got this one's Sp overlapping there and another Sp coming out here. But now we've got 2 unhybridized P's on each carbon, so I'm just going to use different colors. One's usually going on the y-axis. The other one will either be coming, it's probably coming out on the z-axis. I obviously can't draw that, so I'll do my best to come up with something that you can kind of see. All right, so now this overlaps to make 1 pi. This overlaps to make another pi. Don't forget our H's in there. Isn't that beautiful? If anyone were to walk in and just see this picture, they'd be like, what? All right, so looking at this, how many sigma bonds in this picture? 1, 2, 3 sigma. And pi's? 2 pi's. So, the synopsis of all these types of bonds can be found on that first page, back here. Sigma bond. Single bond, check, we get that. Free rotation, I showed you with those model kits just a second ago, is you can easily turn the single bonds. They're not locked in position. And then characterized by head-to-head on-head overlap, part of double and triple bonds. For every double or triple bond, you have to have at least, you have a sigma. And then you have additional unhybridized P's coming up to make these pi bonds. Pi bonds found in double or triple bonds, no rotation. They really are only made by empty P's. So here's the synopsis. A single bond, this is on a Lewis dot structure. A single bond is a sigma bond. A double bond is a sigma pi. And then a triple bond is a sigma pi. Y'all good? For the sake of time, in lieu of drawing new pictures on this page, I want you to go back to the number 26, where we drew our first, from yesterday, these pictures. What we're going to do is add to what we're looking for. On number 26, we're going to add hybridization and how many sigma pi bonds we can find. And I'm going to do them in black. So looking at I, SO3, what is the hybridization around the central atom? 3 areas, so sp2, good. You talk, but you were right this time, so that's okay. And then how many sigma bonds and how many pi bonds? 2 sigma? 3 sigma. Remember, double bond has a sigma and a pi. And how many pi's? 1 pi. Okay, this guy. SO3 minus 2, our sulfate. No, sulfite, excuse me. There's 1, 2, 3, 4 areas. 4 areas. So it's Sp3. And then go ahead and tell me how many sigmas and pi's. Any pi's? Nope, no pi's. Life would be sad without pi. And I don't mean 3.14. I mean like key lime and chocolate coconut meringue. Pecan? Yeah. Pumpkin. People like rhubarb, I heard too. I've never had one. Okay. I shouldn't have got them y'all started on food. We'll get back to food. Let's finish the lecture. All right, this one has how many areas? Not 2, Julian. No, 5 areas. Remember, our lone electrons count as areas. So that would be what hybridization? No sp4, no such thing. sp3d. And then what would be our number of sigma? Was that Jasmina? I told you not to talk for a reason. sp4, whatever. All right, and so what's the number of sigma and pi bonds? 2 sigma, no pi. Again, no pi. So let me show you what a typical AP question would look like. Skip all the way to the end. You've got 2 molecules drawn for 2 different problems. All these other pictures that I'm skipping through are pretty much the same thing pre-drawn for you, but I wanted to talk as I drew them. I think it helps you understand them better. So number 28 is a prime example. And consider the Lewis structure for glycine. What are the approximate angles about each of the 2 carbons and the hybridizations of the orbitals on each of them? So let's look at the left carbon. What is the bond angle? The first thing you want to do is count areas. How many areas are there? 4 areas. So what's the bond angle? And they're all bonded areas, so 109.5. Okay. And then what's the hybridization? Sp3. All right, let's do the other carbon. How many areas around that one? 3 areas. So what's the bond angle? They're all bonded areas, so the bond angle is 120. And then what's the hybridization? Sp2. Okay. What are the hybridizations of the orbitals on the 2 oxygens and nitrogen atom? I'm going to disagree, and we're just going to do this oxygen and that nitrogen. Okay, so look at the left nitrogen. Be careful because there are 2 hydrogens attached to it. So how many areas around the central atom? 4 areas. All right, what is our bond angle? Is it 109.5? Whoa, 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 it's not 109.5. They're not all bonded areas. There's a lone pair there. So approximately 107 degrees. Good. And then what would be our hybridization? It's based on the total, so Sp3. Sp3. All right, the oxygen. Total number of areas. 4 areas. Bond angle? About 104, yes, less than 109.5, because there are 2 lone pair areas. And then what is our hybridization? Sp3 still. So you got to think about hybridization representing the electronic structure, okay, the family. What is the total number of sigma bonds in the entire molecule and number of pi's? So let's count. We have 2 sigmas on this nitrogen attaching the hydrogens. 1, 2. 1, 2. Let me use black and erase all of it. And as I count, I'll make a dot. 1, 2, 3, 4, 5, 6, 7, 8. But there's 1 on that pi bond, right? 9. So 9 sigma. How many pi's? There's only 1 pi in that double bond because that's how it goes. All right, last problem. We're going to take each of these atoms and we're going to do hybridization and bond angle. So carbon, first carbon, hybridization, Sp3 bond angle, 109.5. Next carbon, Sp2 bond angle, 120. It's 3 areas, so it's 120, okay? This one right here, Sp3 bond angle, 109.5, nice. The last one, Sp3, 107-ish, because we have that lone pair. That's the only difference between these two statistics. Okay, that's hybridization in a nutshell.